This is the fifth in my video series about forces, and we're going to look at friction and inclined planes. So first of all, friction is just a force because that occurs because surfaces are just rough. If you take a look, here's my picture of some rough surfaces, and if it looks smooth, there's going to be less friction, but at the microscopic level, there'll be some sort of roughness. It's always going to be in the opposite direction of where the motion would occur. So this person is pushing to the right, friction is going to be to the left because motion would occur here to the right. Once again, it's not occurring, but it would occur to the right. It's not just the direction of the applied force, because you might apply a force at an angle of some sort. But right here, he's applying a force horizontally, and the friction is occurring to the right, and the friction is occurring to the left. So it would be the opposite direction. Static friction is just friction at rest. So the term static means at rest. And then kinetic friction is going to be when the object is in motion. So once it starts moving. Just in general, once again, static friction is always going to be greater than kinetic friction. Notice how the surfaces are closer together. They're kind of sitting there in their spot. This is going to cause a little more of this force of friction than this would occur. So once an object starts moving, friction actually goes down initially. And the surfaces are just kind of bouncing off each other, and that's why. Some of the variables you need to know. First one, force of friction. Here's our friction equation. Force of friction is F, big F, little f, and the unit's going to be the Newton. Coefficient of friction is a mu symbol. That's this little mu looking symbol. And it has no unit. And then the normal force is going to be just normal force, which we'll see in a second. On a flat surface, on a horizontal surface, now we're going to go to inclines at the end of this lesson. On a horizontal surface, the normal force will be nothing more than the weight. So normally, in some basic equations, you find the weight, you know your normal force, except the directions are going to be different. Weight would be the earth pulling it in. Normal force is going to be the ground pushing back up against that object. So just note, you may have to start with FW equals mg to do a lot of these other things. Like if you can find FW, you can then go ahead and find Fn, and Fn will go into this equation, and you'll probably either read in the question or look on a table for the coefficient of friction. You'll determine if the object's actually moving or not, and then you'll solve for force of friction. And then from there, you can solve for acceleration, you can do 1D motion problems, just a lot of other things you can go to from there. Okay, so different types of friction variables. There's static friction. This is just going to be not moving friction. There's kinetic friction. This is going to be friction between two objects that are sliding across each other. And then there's this other thing, which we're not going to deal with mathematically here, but there's rolling friction. So this is not a car that would be trying to stop. If a car is trying to stop, we would actually be dealing with static friction. But a car just moving along the street is going to have some sort of friction between its wheels and the concrete. Another thing to note, take a look how this equation is set up. If this goes up, the mu goes up, the force of friction goes up. So the coefficient of friction is directly related to the force of friction. If you take a look at this table, the greatest friction that we would have occurring would be rubber on concrete. Once again, it's only this table. There might be some other ones too. Rubber on concrete is 1.0 when it's static or not moving friction. So just note, look at this. Static friction for wood on wood is 0.25. Kinetic friction is 0.20. Wood on brick, static is 0.60. It decreases to 0.45 when the object starts moving. And then rubber on concrete is 1.0, and it decreases to 0.80 once the object starts moving. Another thing to note here is when you solve for force of friction for static friction, you're actually solving for the maximum amount of force before an object would move. So often the force you're pushing on an object, it's not moving. There's a good chance you're not pushing it as much as it would need to move, and you might not even be close to that. So if there's a force applied and the object's not moving, well, that would have to be the force of friction. But if you actually solve for the force of friction, once again, for that one, it would be the opposite direction. If you actually solve for the force of friction, you're solving for the maximum amount right before the object starts moving. So if this is static friction, this right here, this right here is telling me how much I would have to push, and if I pushed a little bit more than that, the object would start moving. Whereas this, if I'm just asking for force of friction, whatever you apply is going to be the force of friction if the object's not moving, up to the point where it starts moving, then we do something else. Okay, so watch out for constant motion in this unit. Constant motion means there's no net force, which means there's no acceleration. So the if this person right here is pushing that box across the ground, it's just moving, it's not speeding up, so it's not accelerating. That must mean that the net force is 0, which means the force of friction must equal to the force applied. And just watch out, if there is a net force, which is not the case here, it would cause acceleration, it would cause a change in velocity, not just the motion itself. And so there's usually some multiple choice questions here and there that try to catch students off guard by just saying motion, and then there's another choice, it's acceleration. Acceleration would be the better answer if there is a net force that is, they might say non-zero or greater than 0. So let's take a look at this scenario. It takes us 45 newtons of force horizontally to move a wood block constantly across a desk. Well, let's look at this picture. There's your picture. 45 newtons of force to move this block constantly. Watch out for that, because constantly means that there is no acceleration. And no acceleration means that there's no net force. And therefore, for there not to be no net force, the force of friction must equal to the force applied. So therefore, we can answer all these questions. What's the applied force? That's what we started off with. That's the 45 that was applied. It's constant motion, so therefore the force of friction must balance that off. What's the acceleration? Well, there's no net force, so there's no acceleration. And kind of going back to it, there's no net force as well. So just watch out, constant motion. Could be a trick question, but watch out. Constant acceleration and constant motion are two different things. Constant acceleration means there is an acceleration. Okay, then now let's get to some math, just the normal math problems that would occur with a basic horizontal friction problem. Here you have a 1.5 kilogram wood block on a wood surface, and you're trying to find, it's at rest, you're trying to find how much force would be needed minimally to move it. So since it's not moving and we're trying to find out the minimum to move it, we want to find this maximum amount of friction that would occur before the object would start moving. So we're going to be using static friction for this problem. So minimum is to move up till it's still not moving. So we're using static friction. You're going to find the normal force by finding weight. We'll start with that. So we find the normal force. Well, we need this is not exactly weight. It's going to make a big difference when you're on a horizontal surface. So we're trying to find the normal force. We find weight and mass times gravity. We're going to use 10 here. So this block was 1.5 kilograms. Its acceleration due to gravity was 10, so it has a weight of 15 newtons. So now we know this part. Next part, what you want to do, because weight is, when normal force is directed up, it's just going to be the same thing but directed up instead. Now we want to find the force of static friction. So it's static friction, it's wood on wood, so therefore here's our coefficient of static friction. We go to the equation, we plug in our numbers, 0.25 is the static friction, coefficient of static friction, and we get 3.75 newtons. So that's the force of friction in this situation. Okay, now, once it starts moving though, things change. The force of friction decreases. So how much force would it take to keep a 1.5 kilogram block of wood moving at a constant rate after it's moving? So initially, if you're pushing this wood block, you're going to have to push it a little harder just to get it moving. But once it starts moving, to keep it moving at a constant rate, you would have to apply less of force. Let's find out what that less force is going to be. So we go to the same equation, but now we have kinetic friction. We have the same normal force because it's the same 1.5 kilogram block. So you have your normal force of 15 newtons up. We're going to plug that in right here. And we're going to take our kinetic friction, we're going to plug that in right there, and we get 3.0 newtons of force, which would be the force of friction once the object is moving. So notice how we did require 3.75, really probably 3.751 to get the thing to accelerate to where it started moving, and then from there to keep it moving at a constant rate, we would just have to apply 3.0 newtons from then on. Anything more would cause an acceleration, anything less would cause a deceleration to the point where you might have it stop. Okay, would a 15 kilogram brick on a wood floor accelerate when 120 newtons of force is applied? And then if it is, we're going to find the acceleration. So let's start off, and we want to find out what the net force of this 15 kilogram block is. We're going to use the 10 meters per second squared as our acceleration due to gravity. And we get a weight of 150 newtons down, and therefore that gives us a normal force of 150 newtons up. So we go to our force of friction equation, and we find wood on brick, Brick on wood, wood on brick, same thing. And it is, what is it accelerating? Let's find out if it is actually, if there's enough force to get it to accelerate. Let's find out what the friction is. To find out the friction, we go ahead and take that normal force we solved for. We take our coefficient of static friction and we get 90 newtons. So by looking at this, 120 newtons of force is applied, so 90 newtons of force is kind of going back on it. And yes, it would accelerate since 120 newtons of force is greater than that 90 newtons. So let's find out what the acceleration would be. So we just kind of, it wasn't a waste of time. We had to do this in order to find out if it was moving in the first place. If it wasn't moving, you might not get the answer right. Because remember, you might not be applying enough force to get it to move. So it's never going to move constant if you never got to move in the first place. So what's the acceleration going to be? Would a 15 kilogram brick on wood floor accelerate when 120 newtons of force is applied? Let's figure it out. So we have to restart. We have the same mass, the 150 newtons, but now we have a moving brick. So therefore, that coefficient of friction is less. It went from 0.6 to 0.5 in this case. And when we solve for all of that, we get a force of friction of 67.5. I already kind of clicked ahead. And then we want to figure out what's the overall. So here's our little picture of what's overall happening. 120 newtons of force is applied. There's a force of friction of 67.5 newtons backwards. We take a look at the whole situation. We add 120, we subtract 67.5. Didn't tell us what direction it was moving, so we'll say right is forward in this picture. And so the net force is 52.5 newtons forward. From there, we can figure out the acceleration going to our F net equals ma. I just left off the F net. And we range that A equals, divide out the m's, we get A equals F over m. F is 52.5, once again going to the net force. It's not these forces that cause acceleration, it's the overall. And we have our mass, which we solved for, well actually they gave it to us in the first place, 15. And we solve for it and we get an acceleration of 3.5 meters per second squared. Okay, and then here's another question. If you lift the side of a desk, creating an incline until the moment the object starts moving, what would happen next? Keeping that exact same angle and why? Think about it for a second, pause it, answer it, and you're going to see the answer in a second. Okay, so the block would accelerate down the incline, and this is why. Notice how as the incline increases, the force downhill is increasing. And as soon as it starts moving, the force of friction decreases because kinetic friction is less than static friction. So you're already at an angle that's going to have a net force downhill, and therefore net force causes acceleration, not just motion. And so that's the main point there.